Hey everyone, and welcome back to BlackboardAI. Today, we are tackling a problem from the Epic Institute of Technology Round Summer 2025. Specifically, Codeforces Round 1036, Division 1 plus Division 2, Problem A, Deranged Deletions. It is a fantastic problem that might initially seem complex, but has a beautifully simple solution. Let us dive in. First, let us understand the core concept. What exactly is a derangement array? The problem gives us a precise definition. An array B of length m is a derangement if, when you sort B into a new array C in non-decreasing order, then B sub I must not be equal to C sub I for all positions I from 1 to m. Let us look at the provided examples to solidify this. Example 1, B equals 4, 8, 3, 1. If we sort this, C becomes 1, 3, 4, 8. Now let us compare element by element. B sub 1 equals 4, C sub 1 equals 1, not equal. Good. B sub 2 equals 8, C sub 2 equals 3, not equal. Good. B sub 3 equals 3, C sub 3 equals 4, not equal. Good. B sub 4 equals 1, C sub 4 equals 8, not equal. Good. Since B sub I is never equal to C sub I at any position, 4, 8, 3, 1 is a derangement. Example 2, B equals 3, 2, 1. Sorting this gives C equals 1, 2, 3. Comparing elements, B sub 1 equals 3, C sub 1 equals 1, not equal. B sub 2 equals 2, C sub 2 equals 2. Uh-oh, they are equal. Because B sub 2 equals C sub 2, 3, 2, 1 is not a derangement. The operation we are allowed is simple. We can delete elements from our initial array A. A crucial point is that the relative order of the remaining elements is preserved. Our ultimate goal is to determine if it is possible to perform some, possibly none, operations such that the remaining elements form a non-empty derangement. If yes, we output yes, followed by the length k of our new array, and then the array elements themselves. Otherwise, we output no. The input n is fairly small, up to 100. This problem comes with a very valuable hint. When is there definitely not a solution? This is often the key in competitive programming, looking for the impossible cases first. The hint leads us straight to the crucial no case. If the original array is already sorted in non-decreasing order, for example, 1, 2, 3, or 1, 1, 2, 3, then any sub-array formed by deleting elements will also be sorted in non-decreasing order. Consider this. If you have 1, 2, 3, 4, and you delete 2 and 4, you are left with 1, 3. This is still sorted. And as per our derangement definition, if an array B is sorted, its sorted version C will be identical to B. This means B sub I will always equal C sub I for all I, directly violating the derangement condition. Therefore, if the initial array A is sorted non-decreasingly, we can never form a derangement. This is our definitive no case. So, what if it is not sorted? If it is not sorted, it must contain at least one inversion pair. What is an inversion? It is a pair of elements a sub I, a sub j, where I comes before j in the array, meaning I is less than j. But a sub I is greater than a sub j. For instance, in 4, 8, 3, 1, the pair 8, 3 is an inversion because 8 appears before 3, at index 1 and 2 respectively if 0 indexed, but 8 is greater than 3. This leads us to the ingenious solution for the yes case. If it is not sorted, we simply need to find any such inversion pair. Let us say we find a sub I and a sub j where I is less than j, and a sub I is greater than a sub j. We can choose to keep only these two elements, forming a new array B equals a sub j. Now, let us test if B is a derangement. 1. The sorted version C of B would be a sub j, a sub I, since a sub j is strictly less than a sub I. 2. Is B sub 1 not equal to C sub 1? That is a sub I not equal to a sub j. Yes, they must be different because a sub I is greater than a sub j. 3. Is B sub 2 not equal to C sub 2? That is a sub j not equal to a sub I. Yes, again, they are different. Therefore, any pair of elements a sub I, a sub j, that forms an inversion, when extracted from the original array, always forms a valid derangement. This gives us a wonderfully simple and efficient algorithm. 1. We iterate through the input array from the first element up to the second to last element, that is, I from 0 to n minus 2. 2. For each I, we check if a sub I is greater than a sub I plus 1. This is the simplest type of inversion, an adjacent pair that is out of order. 3. If we find any such I where a sub I is greater than a sub I plus 1, we have found our derangement. Output yes, output 2, since our derangement has two elements, output a sub I followed by a sub I plus 1. We can then stop processing for this test case. 4. If our loop finishes without finding any I where a sub I is greater than a sub I plus 1, it means the array is completely sorted in non-decreasing order, for example, 1, 2, 2, 3. In this case, output no. Let us quickly trace this algorithm with our earlier examples. A equals 4, 8, 3, 1. Check I equals 0, a sub 0 equals 4, a sub 1 equals 8. Is 4 greater than 8? False. Check I equals 1, a sub 1 equals 8, a sub 2 equals 3. Is 8 greater than 3? True, we found an inversion. Output, yes, then 2, then 8, 3, and we are done for this test case. A equals 3, 2, 1. Check I equals 0, a sub 0 equals 3, a sub 1 equals 2. Is 3 greater than 2? True, we found an inversion. Output, yes, then 2, then 3, 2, and we are done. A equals 1, 2, 3. Check I equals 0, a sub 0 equals 1, a sub 1 equals 2. Is 1 greater than 2? False. Check I equals 1, a sub 1 equals 2, a sub 2 equals 3. Is 2 greater than 3? False. We have iterated through the entire array and found no a sub I greater than a sub I plus 1. This means the array is sorted. Output, no. The runtime complexity for this solution is incredibly efficient. We simply iterate through the input array once. This makes it in big O of n algorithm for each test case. Given n up to 100, this is almost instantaneous. The memory complexity is also minimal, just big O of n to store the input array. And there you have it. A seemingly tricky problem, deranged deletions, boils down to a simple check for an adjacent inversion. The key insights came from a careful reading of the derangement definition and understanding the power of the hint. If you found this explanation helpful, please hit that like button, subscribe to BlackboardAI for more competitive programming problem breakdowns, and let me know in the comments if you have any questions or other problems you would like us to cover. Thanks for watching and happy coding.